We are right about to abandon 2 dimensions and move into more exciting stuff. But there is still one 2-dimensional thing to take care of. In 2 dimensions, the state space, we're talking about possible states of a system. In 2 dimensions, the state space can live in a plane. That's natural when you have translational invariance of your motion, or if you're looking at something localized and you don't care about how things look far away from the center of action. Then we found out that when we look at, let's say, a pendulum or Josephson junction, the phase space is a cylinder plane, looks something like that. There are 2 coordinates, let's say x and y. When we look at the pendulum, one of coordinates, the angle of the pendulum is naturally bounded to 0 to 2 pi. It suffices to describe it on a circle. But the other coordinate, which was the rate of change of your angular velocity, is not bounded because it turns out there's something called diffusion, angular diffusion, that if you kick it right, you can make it arbitrarily high. So in this direction, the coordinate is a real minus to plus infinity. So that's a cylinder. And we have the third thing, a bagel or donut or torus. And that's a 2-dimensional surface that in one direction has some extent, let's say 2 pi, but it could be anything. And the other direction, you cut the bagel this way or that way, it has also an angular coordinate. And for such a system, the equation in 2 dimensions, if it's of our canonical form, saying we have 2 angles and first order equations, which is what we always cook up dynamical systems to do, are given by 2 angular velocity functions. That Strogatz called f's for functions. In general, they depend on where you are on a bagel. However, these functions have to be periodic in the angular variable, so you stay on the circle. In both of them, doubly periodic, because you're on a torus, you can go further. And that's why, all the examples you'll see will be full of trigonometric functions, because they are periodic on the desired domain. Now that looks totally contrived, but not so. We move back to 1670. Huygens, because he is a Dutch and every Indo-European language is weirdly pronounced, and Dutch is one of the worst. So Huygens in 1670 gets sick, as people used to do more often in the old times than they do today. And that gives him some time to lie on his bed and stare at his clocks, because he was a great clockmaker. And he notices a weird thing. There are 2, clocks with pendula, old-fashioned clocks in his room. And they're perfectly synchronized, which is very strange because it's very hard to make accurate clocks, and to make clocks which are accurate for arbitrary long time is impossible. So he starts wondering, what is it about? And this is his sketch. There are 2 chairs. There is a board and 2 pendula clocks hanging on it. And there is his attempt to understand what's going on. So these are positions of left clock, right clock, clock A, clock B. You don't know how lucky you are. Huygens, one of the great minds of 17th centuries, they didn't have mathematics, at least the physicists didn't. So it's extremely tedious to read how they thought about it. So instead of writing sines and cosines like any person who had 20 years of schooling and is indoctrinated in Newtonian way of thinking, this is pre-Newton. So he says, well, B has gone again through position C when A is at AG, whereby suspension A is drawn to the right, and therefore the vibration pendulum is being accelerated. B is again in BK when A is returned to, and this goes on and on. This is in his collected works. But, his intuition was right. What's going on is because this pendulum is moving, it's causing a vibration of the board on which the other pendulum hangs. And in his observation, they're locked in the exactly opposite motion. They went away and toward each other. So that's how Huygens thought about it, who was first one to think about it and had the right idea. But you are so lucky that you can just write an equation and we don't have to say this guy moves left, right, and all that. So the equation was a simple case. It says, I have two clocks and they are not identical clocks, but they're perfect within their design. So they have two frequencies in general are different because it's very hard to make them exactly the same until modern times where you use crystals in your watches and computers, but not in mechanical clocks. And then there is this board. So what do we do with this board? There's some kind of oscillation. And in general, any periodic function should be a sum of Fourier components, lots of sines and cosines. But let's assume that the most important is the lowest vibration of the board and not weird high tones when board wiggles many places. So there is some trigonometric function, let's say sine, that models interactions. And now, in general, there is no reason why one phase should be preferable to the other phase, especially if you're not working with a pendulum, but you have something that rotates in a plane, which is the next example I'll have. So assume you have translation invariance, in which case things only depend on the differences between, or the distances between the state space point. And now by symmetry, permutation symmetry, this guy depends on minus theta 2. And this effect of the other clock has some strength, which is something that maybe you will experimentally try to determine. And your intuition, these guys are comparable, but they don't have to be. And so far you have used not much periodicity and translation invariance. So that's a starting point for lots of modeling of couple oscillations. Now, today you care about coupling between breathing and heart, or your circadian rhythms and the motion of the planet, or there is a zillion of oscillatory problems in modern science, engineering, which have this nature of being coupled. So this is, I introduced some completeness argument, this should be a torus, but actually torus is very natural because you can think of it this way. You can think of the first guy running on a circle. So there's some circle And there is, let's say, a runner, a skateboard, whatever, which is in this circular training ring at some angle, theta 1. And there is her friend training on the next track. She's also running. So, you know, putting them kind of overlaid, but if you think of circular tracks, you know, both of them were running in circles. It's a different runner, so it has a different speed of moving. And you can draw this, represent this in many ways. So you can say, well, let me imagine there were two planes. So in one plane, she runs, and in a perpendicular plane to that one, I run. And as long as they're independent, they don't see each other, it doesn't matter how you draw this stuff, but it might be more convenient when you think of couplings. If I stop here and I look at the other runner, she runs on a circle. If I go, also she runs on a circle that's rotated by. And if you think that way, you realize that the natural object to draw is a torus. And on this torus, you put two curvilinear coordinates. You either move in this direction, and you call this, you know, P2, or you move in this direction, and you call this T1. Now, this is a little bit hard to look at. So what people do is they take this bagel, or let's say a car tire, and they slice it on equator. Doesn't matter where you slice it, but you just have to take a hole cut this way. And then you get a two-dimensional ring. Then you slice it someplace this way. And now you have a plane, and it's a piece of rubber. You can, you know, lay it out in front of you, and that's easier to look at. And now what happens in that plane, you have two coordinates, this way. And the hard thing to appreciate is that the opposite walls are identical, because you open it, that was totally artificial where you cut it. So this is the same as that. And this is the same as the opposite wall. When you look at some trajectory, you know, ant moving around the bagel, it might look like that. Anytime it approaches this artificial end and crosses it, it just re-enters at the opposite end in this picture. But this is really the same point. So if curve is smooth, the slope should be smooth, etc. And it goes on until it hits this other cut. Then it re-enters. So here we go from, you know, suppose I started here. I re-entered at 1. I got to this artificial cut. I re-enter, I move, and go to 3. This is supposed to be described by dynamical system. So one thing that, you know, should be absolutely true about these motions, I'm not allowed to cross trajectory with itself, because it means at a crossing point, I wouldn't know which way to go. So determinism says, yes, I can wrap up something on the torus, but it has to be done in such a way that it never crosses itself. You know, very strong constraint on what kind of trajectories you can have. To develop a little bit intuition, you know, we constantly cheat. So we always develop the intuition by first looking at one-dimensional cases stacked together. And here we can cheat even more. Let's forget about the coupling. So we set k = 1. k equal 2, this coupling strength to be 0. So now I have two uncoupled oscillations, rotations. They're just linear equations. In one direction, I move with angular velocity of frequency 1, and in the other one, I move also with constant angular velocity omega 2. That equation I can solve. So theta 1 is wherever I started at time 0. And I integrate both sides and I get plus omega 1t. Same for the other guy. I start any place on a torus. That's my initial point. And then I move with angular velocity omega 2 for time t. So I end up someplace on a torus. And the whole thing should be, this is not good. This can run over larger than 2 pi. So I have to take modulo 2 pi of this side to make sure that I have a periodic function defining on torus. There are two interesting cases to consider. One is if these guys, for some reason, happen to be in a rational relation. So if omega 1, omega 2 is actually a rational number, let's say integer p over integer q, which are relative primes, so two integers. Then what happens is the following. Let's just be lazy and start in the lower left corner, totally artificial point. Every other point would be equally good for this purpose. And now what's happening is that my first variable, which is proportional to p, is growing with some number times p, because they're defined only up to a ratio, so each one of them could be constant. It's growing like this, and then starts here, goes there, and it's just a straight line. It's moving parallel to that modulo 2 pi, and then because of this rational relation, it actually ends up initial point. Remember, this is that and this is that, so this is the same point. And now when you think of it a little bit, what this integer means is that by the time I've closed the period, I've found the periodic solution of this equation. I have turned 2 times 1, 2 around one direction on the torus and 3 times around the other direction of the torus. So in this case, there is a rational relation between these two velocities. Intuitively, this is right. Suppose in given amount of time, you complete 2 runs around the circle, but she completes 3. If you start at the same time, by the time that time elapses, you will both be at the initial point. So you are on a periodic orbit in 2-dimensional space. And that's true of any rational numbers. Now, rational numbers are very fragile. If you perturb them by anything irrational, transcendental, normal, etc., you will get numbers that are normal. And if you care about the measure of rational or irrational numbers, rational numbers are so weird that they measure 0 on a unit interval, and everything else is done by irrational numbers. To you, it might sound like stupid empty mathematics, but actually, when you look at stability of solar system, it turns out it's very important, because it's this kind of phenomena that's giving us the rings of Jupiter and Saturn and other resonant frequencies in the solar system. They come So this plus the coupling, which we'll discuss next. So what happens if you just happens to take two, what we call normal numbers that you take out of hat on a real line, they will have no rational relation. And what will happen for them is that you will start someplace, let's say here, running again constant at some slope, which depends on the ratio of these two velocities. And you will re-emerge because you're, just at the far end of the bagel and you're re-entering our vision again. And you will just keep going. And you'll discover that the entire torus is being filled out so that if I take any little neighborhood, any place on a torus, if I wait long enough, this trajectory will enter it. Not only that, but it'll enter it infinitely often, no matter how small that neighborhood is. So that has a misleading Greek name coming from word energy. It has to do with statistical mechanics and Boltzmann, but it's called ergodic. Now that's a subject of mathematics, understanding ergodic systems. And this is the simplest example of ergodic system. You can have just a linear motion on a torus, and that motion will explore completely the state space. But then there are all kinds of subtleties about, this ratio might not be rational, but it might be one of the many weird numbers which you can express in terms of continued fractions, and they're called Liouville numbers and God knows what. And again, tenures, Fields medals, all kinds of things happens. But we are practical people, so we move on and say, okay, that's example of two Huygens clocks when there is no coupling. Now let's stick some coupling. Let them act on each other. So now we'll say that this coupling term is strictly away from zero. Obviously the important thing is the difference between the two runners, angular distance, because sine is a nonlinear function of that. So let's subtract these two equations and just study the difference. So let's look at phi. How far am I ahead of her, number 2? So that's called phase difference. Take time derivative of both sides. So you subtract these two equations. And you notice that this difference here is minus phi, because phi was defined in this way. So the equation has a minus here when I subtract two of them, but it has K1 plus K2 here, the sum of strength coupling strengths. And what happens? The first thing we can say, well, if this difference is larger or much larger than the prefactor of sine 1, then I cannot reverse the velocity, because if this is bigger than this term, this oscillates between plus and minus of this thing. So for k's which are weak, there'll be change in what trajectory look like, because this theta will speed up, etc. So when I look at my old trajectories, which are straight lines, now the integrals will have some periodic oscillation on them. I'll get a bunch of wiggly spaghetti. But topologically, meaning as far as the shape of solution is concerned, nothing dramatic will happen until omega's, this difference and this is exactly equal. What will happen here is that there'll be some kind of tangencies and bifurcations, and you'll not be surprised. The bifurcation will be of saddle node type, but that I'll skip over that. It's just same as everything we've been doing before. And let's look at the other regime where they're very strongly coupled. I really care about my friend and I want to follow her closely. So this coupling is overwhelming the tendency to just move forward. When that happens, you can see that phi dot, the velocity can be zero when there are values of sign between 1 and -1, where they cancel each other, these two terms. And you get two fixed points, two equilibria. If I plot the relative change of relative angle between two of them as a function of phi, I'll find a constant minus sign multiplied by this magnitude. And that magnitude is sufficiently well that I will reverse my velocity. So, here I'm moving in a right-hand direction, but here I'll be moving backwards. And the usual thing will happen. I'll be stable, here unstable, and so on. So it says that when you look at tori, two things can happen. Either you just keep running around forever, or you get a stable, unstable pair. And now you can use the zero velocity condition to write zero velocities sign. And the condition on the phi is such that its sign makes this vanish. In other words, I can write sine phi in terms of parameters of the two clocks and their couplings, mutual couplings. When you're there, then the oscillators are locked, with each other, meaning the whole system is just moving at one oscillation. And that oscillation you can write either in terms of one or in terms of the other one. And now I can use my equation for the original oscillators, not just the phases. I can use these equations. For example, for the second one, I do this. And now I have a formula for sine theta, so I can eliminate it, and I get expression for the locked frequency as a function of the original independent frequencies, but now it's weighted by the coupling strength. And you look at this formula and you see what does it mean. Let's assume that K1 is bigger than K2, maybe dominant, much bigger. Then I can plot in a frequency space. I can assume that omega 2 is smaller than omega 1, the frequency. And if I look on the frequency axis, these guys are there. And if K1 is very dominant, then, I can start neglecting this stuff. So I'll be approaching omega plus, but I can never exceed it. The locked frequency is some compromise between the two velocities. And if K2 prevails, then I'll be closer to it. And in a physical case, you would say, well, I don't see any reason, why this clock would couple to the other one with different strength. You were expecting the same clocks hanging on Huygens board on the two chairs, K1 equals K2, and the frequency is just the obvious thing in the middle. That's obvious. So that's how dynamics works. Now, because this is solving a differential equation in plane and you're not allowed to cross itself, the result is very boring. This frequency is constant, the locked frequency. So you have two solutions. You have a solution which is the attractive one, from this plot here. And that one, just runs at 45 degrees, it's constant. So it just comes in and out. And it could be some other winding, that's fine. And then there is an unstable periodic orbit on the torus. And the flow is the usual one, you're pushed from unstable towards stable, you're pushed, and eventually, no matter what you do, system blocks and it just works like one frozen clock and not two independent clocks. When you really do this in biology, population statistics, or many other, population theory, many other subjects,